Now, instead of adding just two operands, what do we want to do? We want to add multiple operands simultaneously at the same time. Okay, why do we want to add multiple operands? So, multiple operands, you will see multiple such applications across. So, for example, in our regular daily life, we have seen that whenever we do Excel kind of additions, so whenever you go and buy n number of things from the market, so you have to add all the n numbers together. It's not that we will only add two numbers and then we'll give the output, then again add two numbers. So that's not the way. So there would be good number of scenarios where we would like to add n numbers simultaneously. Now let's say we have to add four numbers, okay, and each of them are of 4 bits. So the numbers are x, y, z and w. So whatever we have learned, based on that, if we want to add these four numbers, what would be our technique? Why we will basically do a step 1 where t1 would be generated, where t1 is equal to x plus y. So what would be our naive approach? In the naive approach, we will add 4 bits of x and 4 bits of y, and we'll put it in an intermediate, let's say, signal. So that signal will say what would be the size of that. Now we have to consider that Cout is also part of the result. So instead of calling it Cout, we will say that it's a 5-bit number. The 5th bit is actually Cout. So whatever is the carry generated, that becomes the 5th bit. Similarly, now whatever is the result, to that result now we should add Z. Now the first operand then is 5-bit, another operand is of 4-bit. If we add both of them, then in the worst case it could be a 6-bit operand, 6-bit output, so 0 to 5, so that would be a T2. Now we still have to add W, so in T2 W would be added, and I'm still writing my sum as a 6-bit number. Why so? Because that will see. So essentially, if this is the method, then overall delay would be equal to I, because I require 4-bit adder. So it's not actually 4-bit adder, it's actually 6-bit adder. Here this was a 6-bit adder, here also this was a 5-bit adder. So let's say on an average delay of 5-bit adder into 3 times, because once this addition is done, before this addition is done, we can't start the second addition. Similarly, till this addition is done, we can't start the third addition. Delay would be, so delay of this combination would be 3 times into delay of 6-bit adder. So 6-bit we are taking it conservatively. Although the step 1 would require only 4-bit addition, the step 2 would require 5-bit addition, and step 3 would require 6-bit addition. So we can, otherwise we could also have taken average of delay of 5-bit adder, but let's say delay of 4-bit adder plus delay of 5-bit adder plus delay of 6-bit adder, that way also we can say. Similarly, area also we can say delay area of 4-bit adder plus area of 5-bit adder plus area of 6-bit adder. So this is going to be area and delay of this. And yes, the question, how do we know what would be the number of sum bits? So there is a very generic formula here, that if we have n bits in each operand, let's say here it was only 4, and how many operands are there, let's say k operands are there, then the size, then the size like of the final sum will be equal to n plus log 2 k. Okay, so this formula can tell us that what would be the size of our final sum. So here total number of operands were 4, and the each of the operand was of size 4. So essentially the sum size of my final would be final result would be 6-bit. So that's why I have taken S equal to 5 to 1, 5 to 0. So that means 6-bit sum could be the output. So now if we have to do this intuitive way where we are adding one by one, why it is taking so much of time? Because every time we are doing this carry propagation, either using ripple carry or carry save adders, carry skip adders, or okay, or parallel prefix adders, but carry is being propagated in each and every addition. And this delay could be huge if the number of operands are large, as well as number of bits in each operand is large. So can there be a better way? So to understand this, the real problem, first we have to understand the real problem. The real problem is again carry propagation. Carry propagation was our problem in our standard addition of two operands also, but here the problem has aggravated much more, because the number of operands has increased, and for every operand, for every two operands, we are propagating carry through the end, and then again we are propagating for the next addition also. So what could be the alternative? Alternative is a carry save adder. In carry save adder, we don't propagate the carry till end, but we save the carry and we propagate only in the end. So once we have calculated, once we have saved all the carries in our last step, then we will go ahead and propagate. Okay, so the idea here would be that each addition will generate some partial sum as well as some partial carry. So these partial carry can also be added through. Okay, so this partial carry could also be added through another partial carry. So finally we can keep on adding all of them, and in the last step, when we have to do propagation is required, then we will do the propagation, and then final sum would be calculated. So the overall advantage would be we would be able to save quite a good amount of time. Now the basic unit here, we would be using our standard full adder or a half adder. Okay, so in the examples what we are going to show here, we would be representing an adder. Let's say I'm representing a full adder using blue, and inside I would write that so in full adder we'll have 3 inputs. So all of these 3 inputs, what power of 2 all of these 3 inputs belong to. So we have to make sure that whenever we are adding any number of inputs in our full adder, they should be of similar power, okay, or similar places. So you remember when we do decimal addition or we do binary addition, we can add only those bits or those digits which are of same place. So if these digits, these inputs belong to one's place, or so belongs to 2's place, then we can add all of them, and then the sum will also be of 2's place, and our carry would be of 4's place. Similarly, if all of them are of 1's place, this is also 1's place, this is also 1's place, in that case my sum would be of 1's place but carry would be of 2's place. So this particular notion we have to remember, and if we use this particular notion, then we can see that how we can use these full adders as a basic building block, and then we try to pack all the computation in less number of delays and less number of basically area. So area as well as delay both can be optimized very efficiently in this carry save adders. So to understand this carry save adder, let's take a simple example where it's not so simple also, but let's try to make it simple. So let's take a simple example where we are adding 16 operands, all of them are of single bit. So basically we are adding all these 16 operands, and all of them are of units place or at one's place value. So what we can do is we can add all of them. We can use our full adders. So if we use full adders, then we can group all the 3 bits at one time, 3 bits at another time. So basically we can use 5 copies of my full adders. each of these full adders is adding units place. Okay, so one particular bit is left behind, so let's keep it like this. Let's try to adjust it in whenever we will get some place or in another set of full adders. So now in this 5 full adders, we are adding all of the units place value, or basically all the 16 operands. Now what we have to see is that the output here, this is of units place, this is of 2's place. Similarly, this is of units place, this is 2's power 1 place, 2's power 0's place, and this is of 2's power 1 place, so on and so forth. So now to add further, we can have another set of full adders, and one half adder will also be required. So what we will do is that we will add all the values which are there at 2's 0 place, and similarly we will also add all the values which are there at 2's power 1 place. So that means now for this particular full adder, I can start from I can add this A0, I can take A0 as one of the input. Similarly, this is also 2's power 0 place, so I can add this also as a second input, and this is also 2's power 0 place, so I can add this as a third input. Now this is 2's power 0 place, this is 2's power 0 place, this is also 2's power 0 place, so I can keep all of these 3 inputs in this particular adder. So this is the input, and then this, and the third one. Now this particular output is 2's power 1 place, this is also 2's power 1 place, this is also 2's power 1 place, so I can add all of them in using this particular full adder, and this, the second one, and the third one, so I can add all of them. Similarly, the remaining 2, this is also 2's power 1 place, this is also 2's power 1 place, I can add both of them also. So using this, I have now created the second stage. So finally we have to add the whatever is the output generated here, so we can finally add them also. Now here I will still require one full adder, two half adders. So in the full adder, I will take this is 2's power 0 place, and this is also 2's power 0 place, so I will add both of these two inputs. I'll take both of them as a input to my this particular adder, this as well as this. Now this is 2's power 1 place, this particular output is 2's power 1 place, this is also 2's power 1 place, this is also 2's power 1 place, and this is also 2's power 1 place. So I have 4 inputs which are of value of 2's power 1 place. So what should I select? So I will select 3 of them. So I will select this one, and this one. So I will select this one, and I will select this one, and I will select this one. Okay, so if we see, this particular output is of 2's power 2 place, so I can add in another half adder which is of 2's power 2. So I can add this. I am taking an orange color for this, and I am adding this 2's power 2 place output is this one, so I will add this one. Now this is the third stage of my 16 operand addition. Now let's see one more stage. So here so what are the, out of these 1 2 3 4 5 6 and 7th one, so we have 7 inputs which are left. So out of them, which one is of 2's power 0 place? 2's power 0 place is only coming from this. This is 2's power 1 place, this is 2's power 1, this is 2's power 2 place, this is 2's power 2, this is 2's power 3 place. So only one input, one output of 2's power 0 place, so I can directly declare that as a result S0. Now for 2's power 1 place, I can add here in my addition which is categorized as 2's power 1 place. So this is another 2's power 1 place which is pending here, I can add this, and the one which was remaining from my previous stage, I can use that also. Okay, So this particular output was 2 to the power 2 place, so I can add it here. This is also 2 to the power 2 place, so I can add it here. The other one will come from here. So this particular addition, when we are connecting this particular carry to the next adder, this particular way of connection is called propagation. So in all other methods we were saving the carry, we were not propagating within the same stage, but here within the same stage we are trying to propagate the carry to the another adder. Okay, so then I can say this one is my sum 1, first bit of sum, and similarly this would be my second bit of sum. Now for addition of 2 to the power 3 places, so there would be two values of 2 to the power 3 places. One is this and the other is which is propagated from this particular carry. So now we can say the output here is this is S3 and this is S4. So as we know that if we are adding 16 operands, if all of them are 1, then the output is going to be 5 bit long. So I would require 5 bits to represent all that. Now we see the last stage is the only stage where we are propagating the carry. In all other stages we are saving and we are simply forwarding to the next stage. What is the delay of this particular whole adder? So the delay would be one full adder delay, second full adder delay, third full adder delay, fourth full adder delay, fifth full adder delay, and sixth full adder delay. So the whole computation can be done using 6 full adder adder delay. And the total area is also quite less: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So overall 15 adders are used. Out of them 11 were full adder and 4 were half adders. If we try to do the same thing known in an intuitive way or in a naive way, we would require 16 additions, one after another. Delay can not be less than 16 full adder delays. But in the later stages, when we are adding, let's say we have already added, let's say 7 operands, after that my output is going to be 4 bit 3 bit sorry 4 bit. So when the output is 4 bit, then every addition would require a 4 bit addition delay. So the delay in a naive approach is very very large with respect to this carry save adder delay, as well as the area is also quite efficient. Okay, so the overall, you may get confused that how do we create these combinations and how do we connect all of them. The whole idea is that we have to always keep in mind that a particular output is what is the place of that particular output. We cannot add 2 outputs which are of different places. So in one full adder, all the inputs should belong to same place, then we can add them, otherwise we cannot add them. The other way to design this kind of a tree structure is that we will try to see how many inputs are there. If number of input to a particular place is more than 3 or a multiple of 3, then we can use full adders. If it is less than 3, it's only 2, then we can use half adder. If it is more than 3, your half adder is not sufficient, you can also leave it like we have left this particular output here. So then we can keep on building from stage 1 to stage 2 and then stage 3, and then we can finally create a whole tree, and we can see how this carry save adder could be created. So let's try to see using one more example. So in this example, what we'll do is we'll use 4 operands of 4 bit each. So this particular example has been taken from this particular book, Computer Arithmetic Algorithm by Koren. So yeah, I'm directly explaining the example. So the method is very similar. So now there are 4 inputs x, y, z, all of them are of 4 bits. So let's say x is x0, x1, x2, x3. So in first stage of carry save adder, what we do is we take all the 3 operands x0, y0, z0, x1, y1, z1, x2, y2, z2, x3, y3, z3, and we add all of them. Now all of them, so here you see a different pattern because x0, y0, z0, they were of 2's power 0 place. These were all 1 of 2's power 1 place. These were all 2's power 2 place, and these are all of 2's power 3 place. So we can add them together because their powers are same. So in the next level of carry save adder, so we whatever is the output of this 2's power 0 place, we can add it here. Now W0 was pending, so this W0 also we can add in the next stage. Here the output of the second output, that means carry output, belongs to 2's power 1 place, so we can add in a carry which takes 2's power 1 place as an input. The sum part of this particular adder is also of 2's power 1 place. Now W1 is also of 2's power 1 place, so we can add them in a full adder which takes 2's power 1 place as an input. So similarly for 2's power 2 place also, the output of this particular addition, carry part of this particular addition, is 2's power 2 place. So similar to this 2's power 2, 2's power 3, the second stage of CSA can be completed. Now after the second stage, there is the only one output which is of 2's power 0 place. We can declare that as S0. The next one, this can be taken as the output here because this is the 2's power 1. Now this is this is another input from 2's power 1, so this is a half adder which we have used here. Sum would be given here. Now the carry would be propagated to the next stage. Now the next stage is taking carry from 2's power 1 stage here, 2's power 1 adder here, and carry of 2's power 1 adder, and sum of 2's power 2 adder. Now similarly, this 2's power 3 adder is taking input from these 3 places, carry of 2's power 2 stage here, carry of 2's power 2 stage, and sum of 2's power 3. So similarly 2's power 4 adder is also taking 3 inputs, one from the carry of 2's power 3 adder, another carry of 2's power 3 adder, and carry of 2's power 3 adder which is there also. So now you see, in this last stage, carry was propagated from here to here, then here to here, then here to here. So this is the last stage where we are doing carry propagation adder. In the first 2 stages, it was all carry save because carry was moving ahead. Within the same stage, there were no 2 adders where we were passing on the carry input from one adder to the other adder. Now delay of this whole 4-bit operands is equal to the delay of full adder 1, delay of full adder 2, plus delay of full adder 3, 4, 5, 6. So total delay is equal to 6 full adder delays. While in our naive approach, we have seen the delay of adding 4 operands of 4 bit was equal to delay of 4-bit adder plus 5-bit adder plus delay of 6-bit adder. But here it is actually 6 full adders delay, which is going to be less. Similarly, area is also quite efficient. The total number of adders we require, full adders we require, is only 12. So this carry save adder presents a good opportunity. It's a different kind of an optimization where we are playing with the bits. We are trying to identify which bits we can add together, which belongs to the same place, and this can give us an optimization which can save both area as well as the delay. So in our previous approaches, like in carry select adders or parallel prefix adders or look ahead adder, we were compromising on area, so we are increasing the area to reduce the delay, but we have seen in this carry save adders we are reducing both area as well as delay for a particular station. But this case is very selective whenever we are adding multiple operands. We'll see in our next lecture that what is the most common use case of these carry save adders, or when do we require to add multiple operands at the same time. With this, let's close the lecture. Thank you very much.